Welcome to Space News from the Electric Universe, brought to you by the Thunderbolts Project at thunderbolts.info. A radical tenet of the electric universe theory, as proposed by the chief principles of the Thunderbolts Project, is that conditions in the inner solar system and planet Earth were vastly different within human memory. Ancient man lived in awe, reverence, and sometimes terror of the planetary gods. If planets and moons, including Earth, move on different courses today than in the relatively recent past, one thing is certain. The gravitational force on Earth has not remained constant since the Earth's formation, supposedly 4.5 billion years ago. If Earth's gravity has not remained fixed over countless eons of time, a clear test of this hypothesis could come in the comparison of life forms in our world today versus those of prehistoric eras. Scientists tell us that for about 165 million years on planet Earth, fantastic and often giant creatures called dinosaurs ruled our world. Of course, the largest of the dinosaurs dwarf any animal that walks the Earth today. Yet consensus scientific theory tells us that Earth's gravity was not weaker during the Mesozoic era. In today's episode, we ask author Ted Holden to explore the controversial question: do dinosaurs pose a gravity problem?
Engineers in the late 19th century had understood well enough that they had a big problem with understanding how a sauropod dinosaur could walk on land, right? I mean, they never managed to put numbers on it. I'm the first person that managed to put real numbers on that. But they knew there was a problem. They were assuming that the sauropod dinosaurs must have lived in water, right? But more recently, it's turned out they had no adaptation whatsoever for living in water. They would have needed snowshoe feet. The feet they actually had would just sink right into the muddy river bottoms, right? I mean, they'd be immobilized almost immediately. The idea of a large dinosaur using his neck as a snorkel wouldn't work. That they finally figured that out. They've got tracks showing dinosaurs, walking easily enough on land, right? I mean, in fact, they have more in the way of footprints than they do of bones in the case of large dinosaurs. They have some. And they keep finding bigger ones. They keep finding bigger bones. They keep finding bigger footprints. So they've got footprints which indicate a creature which would be 200 feet long, which you would call breviparipus. And there's a couple of other things like that. That's the one word that I can remember easily. You've got titanosaurs. Now, it's like, they used to think that a brontosaur was a really big dinosaur when I was a child, right? I mean, they had a brontosaur skeleton in the Smithsonian Museum. But they keep finding bigger ones. The ultrasaur, not even the largest of the titanosaurs, but Christopher McGowan, the curator of paleontology at the Royal Museum in Ontario, has a book out about dinosaurs, and just from purely volumetric calculations, it calculated a weight of 180 tons for the ultrasaur. The question becomes like, what is it that's allowing these kinds of creatures in our world? The first thing that occurred to me was that, we don't really know very much about dinosaurs, how exactly they lived as far as muscle or anything like that, but we know quite a lot at this point about the weightlifting sports, right? And they hadn't made any sort of a science out of the weightlifting sports, in late 1800s, early 1900s, whereas they have now, right? We know what the limits of size for a human athlete would be, right? So, I mean, any kind of a size limit you could compute for the human athlete is also going to serve as an upper bound for any sort of a herbivore the same size. The only other kind of argument you could try to make would be that the dinosaur must have had better muscle than we have. Well, that doesn't work either. Muscle tissue is all pretty much the same under a microscope. I mean, for vertebrate animals, mice, dogs, cats, humans, elephants, it's all pretty much the same. How strong something is just a question of how much muscle mass do you have and how well is it trained. So at that point, you could start to ask yourself, how do you compute like a size limit for the strongest people that we have in the world? And you get into the scaling system that they use for Olympic or powerlifting events, which says that you scale by a general average of cross-section, which is this 2/3 power body weight. Where does that come from, and why would you want to do that? You're talking about square cube phenomena at that point. And we've all seen this, okay? It's like, there was always the littlest kid in your classroom that could do the most pull-ups, or the most pull-ups, or any kind of a ratio exercise, where strength is proportional to cross-section of bones and muscles, and weight is proportional to volume, which is the cubed figure. We know that strength basically varies according to cross-section of bones and muscles. If you know a person's weight and you want a general average of body cross-section, then weight is going to be it's proportional to volume. It's some number times volume. You might have a weightlifting event, say the bench press, for instance, and you've got 6 or 7 or 8 different weight divisions. You'd like to know who had really done the best lift overall. What you do is you divide through by 2/3 power of the athlete's weight in each case. And the numbers all line up. They almost become the same number. One will stand out just a little bit, right? And that's going to be the guy that did the best lift. Whereas if you say, okay, now we're going to go from the realm of real things into thought experiments, and we're going to conduct a thought experiment of scaling the same athlete to different sizes, well, that sort of isometric scaling becomes perfect, right? Because you're talking about the same guy, just making them different sizes. You would like to know, at what size does the square cube thing make one of these top human powerlifters dysfunctional? What you do is you say, okay, we're just going to exactly use this 2/3 power of weight scaling factor. On the left side of the equation, I'm going to say, okay, Bill Kazmaier plus the bar is like 350 pounds plus the 1,000 for the bar, right? 1,350 divided by the 2/3 power of 350 equals, on the right side of the equation, just the guy lifting himself up off the floor, right? Just x divided by the 2/3 power of x and solve, right? You get a number like somewhere between 18,000 and about 21,000 pounds, right? That's the theoretical maximum size limit for the world for one of the strongest athletes that we know anything about. That's the theoretical limit. And the thing that's funny is the biggest elephants that we know anything about are typically 14, 15, 16,000 pounds. Now, I don't think anybody claims to have any kind of a stuffed elephant any bigger than the one that you see at the Smithsonian. And those people told me that elephant was 8 tons, right? It was 16,000 pounds. Kind of interesting that you've got this theoretical number, which I've produced, and it matches up very nicely with the real world number. You would expect the real world limit to be a bit lower than the theoretical absolute maximum, because you're never going to get an elephant that's all muscle. So this is the first little thing that we deduced. It says that there's a theoretical size limit of about 20,000 pounds in our present world. And then you get into another question, which is that other calculation that you see in that paper. Like how much attenuation would you need for something like an ultrasaur to walk around? Well, the observation you make is that walking around cannot have been any more of an effort for the ultrasaur in his world than it is for that elephant in the Smithsonian and his. You see what I'm saying? So if you just equate the two levels of effort, weight divided by 2/3 power mass, we know that the ultrasaur would weigh about 180 tons in our world, and the elephant weighs about 8. The ratio of about 22.5 to 1. You can just substitute one of those ideas into the other, and it's like the constant of proportionality falls out, right? You get a ratio of about 2.8 to 1. That says you would need to have at the very least, a 2.8 to 1 reduction in gravity for the ultrasaur to stand up as easily as an absolute maximum lift effort by one of these top human lifters. That's the basic idea as far as strength goes, but there's more to it than that. You've got other kinds of things you're trying to account for. Every kind of a measure of efficiency, aside from just strength, varies with some kind of a squared figure, right? It's like a bird's ability to fly. It depends on surface area of wings, which is a squared figure. Your ability to breathe is proportional to surface area of lungs, which is another squared figure. Even your ability to digest food is proportional to surface area of your digestive system, which is why some authors have noted that they don't see how anything could possibly become bigger than an elephant in today's world, simply because the elephant has to spend the whole day eating to support his size. You've got a question of birds, which says that the largest birds which can fly in our world are 30, 35 pounds, something like that. That's the biggest thing that flies in our world, right? Now, when you get to 10, 20, 30,000 years ago, they had like an Argentinian teratorn, which was basically a golden eagle with a 25-foot wingspan, a couple 100 pounds, that flew. And then you've got these flying creatures, which are like the Texas pterosaurs, the Big Bend pterosaurs. And those things could have gone like 500 to 1,000 pounds. And they flew, right? Now, when Juan Langston first started working with Texas pterosaur bones, he didn't really have much in the way of wing bones. The bones he did have indicated a wingspan of 60 feet. But more recently, they've actually found more in the way of wing bones for those things, both in Israel and in Mexico. And what they've actually found indicate, wingspan of 60 feet. You've got like huge, huge things flying in ancient times that couldn't begin to fly in our present world. The oldest version of this paper of mine spoke about the pteranodon and the fact that scholars who had studied what was involved in flying had examined the pteranodon and decided that the size limit of a pteranodon had to be the biggest thing that ever possibly flew. So any bigger than that, even just gliding, even trying to hold his wings straight in a turn would snap his wing bones. There's one other kind of a thing which you would want to try to account for, which is the question of sauropod dinosaurs and their necks, right? And I believe that that's the biggest problem of all. You've got two basic kinds of large dinosaurs. You've got what they call brachiosaurids, and then which held their necks upwards according to the bones. And then you've got the diplodocids, right, which apparently held their necks outwards. Now, the largest thing that we have bones for, as far as length goes, which the seismosaur was a diplodocid. The question is, if you've got a neck which is, 50 feet long and weighs 40,000 pounds or something like that, how are you going to hold that neck? If you hold it upwards, then you've got an extreme problem getting blood to your brain, right? And it's like a giraffe's vascular system and blood pressure would blow our vascular system apart. They have a very, very tight skin, which acts like a flight suit, for a jet fighter pilot. Just getting blood up as high as you need to get it for a giraffe is a big problem, right? If you had to get blood up, like 40 feet above your shoulders, you would have a creature which was constantly walking around in constant danger of some sort of a major circulatory system disaster, right? That's no way to dominate the Earth for tens of millions of years.
In part 1 of this presentation, author Ted Holden explored the evidence for fundamental differences in our world's environment since a time when dinosaurs walked the Earth. In Holden's analysis, the most obvious explanation for the enormous size of the largest dinosaurs is that Earth's gravity was once considerably weaker. But the mysteries don't end there. While the Thunderbolts project takes no position on these issues, in this episode, Holden continues his analysis and explores perhaps the most controversial question of all. Is it possible that dinosaurs existed on Earth far more recently than institutional science has ever considered?
Aside from the various problems I may have mentioned in that first interview involving dinosaurs and flying creatures and things whose ability to function depends on something which involves a squared figure, whereas weight is always proportional to volume, which is the cubed figure. In the case of size and strength, as you double your dimensions, you cut your power to weight ratio in half. You can only cut your power to weight ratio in half so many times and still stand up and function, right? You've got a problem with the large dinosaurs, aside from just standing up, you've got a problem with what to do with their necks, right? Because, as I mentioned previously, if they held their necks upwards, they wouldn't be able to get blood to their brains, right? I mean, it would take a heart bigger than their body would hold just to get blood pressure enough to function, right? So that you've got people nowadays trying to believe that all dinosaurs held their necks outwards, but a large dinosaur holding his neck outward would have an even bigger problem than that. In other words, something like a seismosaur, whose neck could easily be 50 feet long, right? Could easily weigh 40, 50, 60,000 pounds. If you've got a neck which is even 40,000 pounds, and if the center of gravity of that neck is even 10 feet out from the shoulders, then you're looking at 400,000 foot-pounds of torque. And you're probably looking at more like 500,000, a bit more than 500,000 foot-pounds of torque for a number of these animals if they were to hold their necks outwards. Now, what exactly is like 500,000 foot-pounds of torque ballpark for? Well, I mean, that's ballpark for the combined maximum torque of all 4 of the engines of an Iowa-class battleship. That is, enough torque to drive a 60,000-ton ship through the water at 33 knots. That's the dilemma. A sauropod dinosaur in our world would have no way to hold his neck. He couldn't hold his neck upwards because of the blood pressure problem, and he couldn't hold his neck outwards because of the torque problem. You've got a couple of other comments on that first video. Some of these I've seen over and over again. You've got a claim that, well, maybe the air was simply more dense in those days, or you had an atmosphere which was close to being buoyant, and maybe that accounted for some of these problems. The answer is not really. I mean, number one, you've still got to breathe that air, right? I mean, air which was close to being buoyant would simply burn up anything trying to breathe it. It would be like the redneck physics experiment where you get the guys trying to pour a pail of liquid oxygen onto a barbecue. That looks sort of like the napalm bomb scenes, from Victory at Sea. And that's what would be going on inside the cells of your body if you were to sit there and try to breathe an atmosphere that was that thick. That's number one. Number two says that, like, even in the case of a 40-pound pterosaur, like the pterodactyl, the pteranodon, in the 1940s and 50s and 60s, that was the biggest flying dinosaur that anybody knew anything about, right? And they assumed that somewhere around 40 pounds was the largest creature that could possibly even glide, much less fly. Is that even just holding his wings in a turn would snap the wing bones if he was any bigger than that. Just in our normal atmosphere, now if you make the atmosphere close to being buoyant, then that problem becomes worse, not better. You've got problems which I think would just eliminate this idea of a vastly thicker atmosphere straight off the bat. The only thing that really helps the situation is reduced gravity. You've also got a question of people wanting to talk about expanding Earth theories. And I mentioned that I do not believe in Earth expanding theories. Why not, right? Well, there's a couple of reasons. Why would anybody want to believe in an expanding Earth theory? There's two reasons. One is dinosaurs. Once you realize that a large dinosaur could not exist in our present gravity, then the simplest way to try to account for reduced gravity in ancient times would be to try to talk about the Earth simply expanding its mass, right? Well, maybe the Earth just was nowhere near as big in ancient times. You've got people making this claim, and they assume that you've got 65 million years to account for this increase in mass going from the world of the dinosaurs to our present age. It turns out that that's not really believable. It's like those 65 million years have gone away. Somewhere around 2006, you started getting soft tissue turning up in dinosaur remains. It started with this Mary Schweitzer at North Carolina State University, who was working with a bunch of tyrannosaur bones. They had one very large femur bone, which was intact. They cut it in half, right? They figured to glue it back together once they got it back to the university. But once they cut this thing in half, they were able to see that there was soft tissue remaining in this bone, and that they've gotten more and more soft tissue starting from that time, not just in the one bone, right, but in a number of dinosaur remains involving hadrosaurs, involving like the Triceratops, involving several other kinds of dinosaurs, right? And, there's no way in the world that soft tissue is going to survive for 65 million years. Okay, they've actually started to get good radiocarbon dates for some of this soft tissue. In several cases, they've gotten radiocarbon dates of 20 to 40,000 years. So that you've got several data points like this. You've got radiocarbon datings for dinosaur remains. You've got good representations of known dinosaur types on canyon walls around North America. And the most common of the dinosaur petroglyphs is the stegosaur, which Native Americans called Mishipishu, which means water panther. You've got like a number of those which still exist. You've got a large animal that holds his legs underneath his body, which means that he's not a crocodile or anything like that, right? He's got dorsal spikes of the stegosaur. Now, Vine Deloria told me he'd been doing a compendium of Indian oral traditions. He'd been up and down the American continent speaking to every storyteller, every keeper of oral traditions, all the way from Alaska down to Tierra del Fuego, right? And he said if there was anything that sort of flummoxed him at first, it was the extent to which almost every one of these tribes retained oral traditions about, Indian ancestors having to deal with dinosaurs. He said that the name Mishipishu means water panther. It's a name similar to the word Mississippi. That Indian oral traditions described this water panther, they call him a water panther, Mishipishu, as having like red fur, a cat-like face, a saw blade back, and a great spiked tail, which he used as a weapon. Okay, Lewis and Clark had said that their native guides were in mortal terror at the sight of these glyphs around the Mississippi River, because the original intention of these glyphs was caution. One of these things lives here. What I believe to be the case, Stegosaur was not the largest dinosaur, but he still had gravity problems, right? It was like, I believe that the Stegosaur moved into water after the change in gravity simply to deal with this increasing weight, but that he didn't have any real adaptation for living in water. He eventually died out. The bull sharks got him or something else like that got him, At the Kachina Bridge in Natural Bridges, Utah, you've got a sauropod glyph, which looks like this. But the evolutionists that are saying, well, this is just a snake, obviously. And these four legs are just smudges. No snake ever coiled himself into a configuration like that. That's a dinosaur.
For continuous updates on space news from the electric universe, stay tuned to thunderbolts.info.